This video will give a brief introduction to the binomial probability distribution for binomial experiments and show how to calculate these probabilities by hand. There's a different set of videos in my feed for how to calculate binomial probability distribution for both the TI-83, 84, and the Casio calculators, as well as how to do it with GeoGebra. So please view those videos if you'd like to see how to calculate these with technology. So let's look at some examples of a binomial probability experiment, and then we'll talk about the distribution. A fair coin is tossed 2 times. Can we calculate the probability of getting 2 tails? Well, if we toss a fair coin twice, we will have 4 sets of outcomes. So we could have heads, 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 tails, tails, heads, tails, tails. And of those 4 outcomes, only one of them will be 2 tails, 1 out of 4. If we look at the probability of getting at most 1 tail, at most 1 means either 0 or 1 tail. So 0 tails would be 2 heads, and 1 tail would be either heads tails or tails heads. So 3 out of 4. And we could find these probabilities fairly easily. If we look at example 4.10, it says a fair coin is now tossed 10 times. Well, let's really quickly look at how many outcomes are possible for 10 tosses of a fair coin. This uses the fundamental counting principle. 5, 6, 7, 8, 9, 10. And the fundamental counting principle basically says the number of outcomes the number of possible outcomes per part of the experiment gets multiplied. So if I first toss a coin once, I can get 2 outcomes. If I toss it a second time, I can get 2 outcomes. If I could toss it 3 times, I'll get 2 outcomes. 4 times, 2 outcomes. So on and so forth. Each time I toss a coin, I have 2 possible outcomes. And we multiply all of these together. And when we multiply all of these together, we would get 2 times 2 times 2 times 2, or 2 to the 10th power. And 2 to the 10th power is 1,024 total outcomes. So if we wanted to find the probability of getting exactly 3 tails, well, we'd have to figure out how many times I could rearrange 3 T's with 7 H's. Well, that could be one way, or I could do tails, tails, heads, 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 tails. Or I could do tails, heads, 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 tails. Oh, this one should have also been a tails. And we can rearrange these in so many different ways that these probabilities become almost unmanageable. So that's where the binomial distribution will come in. Let's look at the binomial distribution. The previous 2 questions are examples of what's called a binomial experiment. There are 3 characteristics of a binomial experiment. The first is that there is a fixed number of trials. In example 4.9, we tossed a coin twice. In example 4.10, we tossed a coin 10 times. Think of trials as the repetitions of an experiment. The letter N denotes the number of trials. So again, in example 4.9, we used N equals 2. For example 4.10, we used N equals 10. And for a binomial experiment, we need to have only 2 possible outcomes called success and failure for each trial. In the previous examples, we said tails was a success because we were looking for the number of tails, whether it was getting 1 tail or getting 3 tails or getting at most 1 tail. There are, the letter P denotes the probability of a success on 1 trial. So in the previous 2 examples, we only had 2 outcomes for tossing a coin. Each one of those had a 50% probability. So P would be equal to 0.5 for the previous experiments. And the letter Q denotes the probability of a failure on 1 trial. Note that P and Q are complements of each other, meaning that their sum is 1. And the third criteria is that the n trials are independent and are repeated using identical conditions. Because the n trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Basically, independent events means that one outcome has no bearing on the next outcome. Meaning if I toss a coin once and get heads, it does not change whether or not I get heads or tails on the second coin toss. Another way of saying this is that for each individual trial, the probability P of a success and the probability Q of a failure remain the same. For example, randomly guessing at a true-false statistics question has only two outcomes. If a success is guessing correctly, then a failure is guessing incorrectly. So let's look at an example of this student named Joe. Suppose Joe always guesses the correct answer 60% of the time. On any question of a statistics true-false test, the probability of a correct guess would be P equals 0.6. Then Q, the complement, would be 0.4. This means that for every true-false statistics test, Joe has a 60% chance of guessing each individual question correctly. If Joe was taking a 5-question quiz, the probability of him guessing 4 or 5 correct answers could be found with all of these possible outcomes. Now there's a whole bunch of outcomes that we could have here. For the first outcome, we could have 2, either correct or incorrect, where I used the letter W for wrong. On the second question, we have 2 outcomes. On the third question, we have 2 outcomes. On the fourth question, we have 2 outcomes. On the fifth question, we have 2 outcomes. By the fundamental counting principle, that means that we have 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 32 possible outcomes for guessing on a 5-question test. And these are all combinations of C's and W's. I use the letter C to stand for a correct answer and the letter W to stand for a wrong answer. So if we look, I listed the 5 different ways that we can get 4 correct guesses and the one way that we can get 5 correct guesses. So we can use what we know about probabilities to calculate all of these. Again, we're just trying to build the idea of the binomial probability distribution. There are future videos that show how to how to calculate these probabilities using the TI-83 or TI-84 calculator, the Casio FX-CG50, and GeoGebra. So we can do these with technology. But for right now, I'm just trying to build the idea of what it is that we're doing. So if we have a 5-question multiple choice test, the probability of guessing the first question correctly is 60%, and the probability of guessing the second question correctly is 60%, and the probability of guessing the third question correctly is 60%, and the probability of guessing the fourth question correctly is 60%, and the probability of guessing the 5th question incorrect or wrong is 40%. Because of our rules of probability, whenever we have the AND connector, we're going to multiply them. So we would get 0.6 times 0.6 times 0.6 times 0.6 times 0.4. If we look at the next set of outcomes, we'll have this similar calculation. The only difference is that the 0.4 is going to move earlier in the order. But either way, we'll have 0.6 times 0.6 times 0.6 times 0.6 times 0.4. If we look at the third possible, we have 0.6 times 0.6 times 0.4 times 0.6 times 0.6. Either way, we have 4 60% answers and 1 40% answer. Then if we look at the fourth option, we have 0.6 times 0.4 times 0.6 times 0.6 times 0.6. And then lastly, we have 0.4 times 0.6 times 0.6 times 0.6 times 0.6. So all of these are the same calculation of 0.6 to the 4th times 0.4. .6 to the 4th power times 0.4, and 0.6 to the 4th power times 0.4. and 0.6 to the 4th power times 0.4. And then for our 6th outcome, if we guess them all correct, or if Joe guesses them all correctly, it's 0.6 times 0.6 times 0.6 times 0.6 times 0.6. There's only one way of writing all C's, and I have them all correct answers. So this would be 0.6 to the 5th power. Now we can use any calculator we want to calculate these. I'll do that off camera. I would encourage you to pause the video now and just confirm that you know how to type these into the graphing calculator or your scientific calculator. So we want to know, what is the probability that Joe gets 4 or 5 correct answers by guessing on this 5-question quiz? Well, basically, what we would do is find the probability that he guesses 4 correctly, and then find the probability that he guesses 5 correctly, and then add those two together to find the total probability. There is a formula, the Binomial Probability Distribution formula. It says NCX, this is a combinations. So NCX is the number of combinations for n trials with x outcomes. So if we had 5 trials, we have 5 ways of choosing. This should be a 5, not a 4. We have 5 ways of getting 4 correct answers and 1 incorrect, or 1 wrong answer. And that's what's highlighted now in pink. 1, 2, 3, 4, 5 different ways of finding them. And each of those 5 ways has the same calculations. It is 0.6 to the 4th times 0.4. So 5 times 0.05184 is 0.2592. 0.2592. Again, I'm doing this off screen with any old calculator. And we could do something similar for the probability of guessing 5 correctly, but that is just 6 to the 5th, sorry, 0.6 to the 5th, which I've already done off camera, which is 0.07776. So to find the probability that Joe guesses the correct answers on 4 or 5 correct questions, we would just find the sum of these two probabilities, which I will do off camera. We will get 0.337. Or if I wanted to, I guess I could go all the way, 696. Generally, we round probability answers to only 4 decimal places. All right, so that's how we would use the binomial probability formula to find the binomial probabilities. Again, I've said this a few times, there are other videos in my feed that show how to do this with the TI-83 or TI-84, the Casio FX CG50, and GeoGebra. We have a little bit more notes to go through here. When the outcomes of a binomial experiment are being sought, we can use the binomial probability distribution. There are some important symbols and formulas for the binomial probability distribution. N is the total number of independent trials. For the correct guess question, N was 5. We had 5 questions on the test. X is the number of successes in those trials. We wanted X equal to 4 or X equal to 5, number of correct guesses that we were looking for. P is the probability of success in one outcome for the previous question. P was 0.6, and Q is the probability of failure in one outcome. Q was 0.4. Next, we can find the mean and standard deviation. Recall that the mean is basically the same thing as finding the expected value for a probability distribution or a probability experiment. So we can answer the question, what is the expected number of questions Joe will answer correctly by guessing on a 5-question quiz? Well, we know that Joe guesses correctly 60% of the time. 60% of the questions guessed are correct. Or I guess I should say answers, not questions. 60% of the answers that Joe guesses are correct. Well, if Joe is guessing on 5 questions, 5 times 0.6 would be 3. We would expect Joe to get 3 questions correct by guessing. Mu is n times p. What about the standard deviation? Well, the standard deviation will be the expected number of questions that change from the mean. So the formula for this is sigma equals the square root of the number of guesses times the probability of success times the probability of failure. We're not worried about where this formula comes from for right now. We're just going to try and find the standard deviation quickly. I'm going to calculate that off camera. While I'm doing that, just notice that all of the values that we are finding here are population variables. They are for the proportion. The reason for that is we are looking at the expected number of questions, which is the mean for all potential outcomes. Since we're trying to find the mean for all potential outcomes, we are trying to find the population mean and the population standard deviation. All right, so that is how you calculate the mean and standard deviation for a binomial probability distribution. And that's how you calculate binomial probabilities for binomial experiments. Please continue watching the other videos that I have posted on how to do these calculations with the graphing calculators.